Thank you, everyone, and good day, all of you. Welcome, all of you, to the tinyML Pakistan Meetup inaugural session. I am Awais bin Altaf, Assistant Professor in Lahore University of Management Sciences, and today we have a talk about SuperSlash unifying design space exploration and model compression methodology for design of deep learning accelerators for tinyML. The talk is going to be by Dr. Rehan Hafiz. He's currently a professor in Information Technology University, Lahore, Pakistan. Please. So next slide. So we would like to thank our strategic partners. So we have Aeon Devices, ARM, DeepLight, Edge Impulse, EMSA, Greenwave Technologies, Grovity, HotG, Imagimove, Latent AI, Maxim Integrated, Analog Devices, Exo, Qualcomm, Reality AI, Renesas, SAP, Seed, SensiML, SynSense, and Sentient. Next. Yeah, now I would like to invite and introduce our speaker. So our speaker is Dr. Rehan Hafiz. Rehan Hafiz received his PhD degree in electrical engineering from the University of Manchester, United Kingdom in 2008. He is currently with Information Technology University, Lahore, as a professor in the Faculty of Engineering. He founded and directed the Vision Processing Lab, VisPro, that focuses on area like vision system design, approximate computing, design of application-specific hardware accelerators, deep learning, FPGA-based designs, and applied image and video processing. Apart from several publications in these areas, he holds multiple patents in the US, South Korean, and Pakistani patent office. We would like to invite Dr. Hafiz to present his talk on the tinyML topic. Please, Dr. Hafiz.
So hello everyone, I am Rehan and welcome to my talk, SuperSlash Unifying Design Space Exploration and Model Compression for the Design of Deep Learning Accelerators for tinyML. Most of the work in these slides are basically related with one of our publication, which is in IEEE TCAD. And I would like to take the names of the contributors. So Zur Ahmed happens to be my PhD student who was leading this work. And I have some MS students at ITU, and we have some of our collaborators. So in this work, we were having a Dr. Shafiq, who was from the NYU UAE. So let's start with the talk. I will start with a little bit of introduction, which relates with the deep neural networks. And we all know that how much they have changed the way we have been doing all the processing, and they have also changed the way we have been implementing the algorithms. And afterwards, we will move on to the hardware accelerator architectures. We will discuss that how do the typical AI hardware accelerators look like. And afterwards, we will also understand that what are the problems in these AI accelerators. And afterwards, we also need to understand some of the concepts which are related with the talk. So we will talk a bit about the tiling strategies and their relation with the design space exploration. Following that, we shall be discussing the SuperSlash methodology of our main contribution and the motivational analysis behind it. And afterwards, we will move on to the results. Okay, so over the past decade, the deep neural networks have allowed us to achieve remarkable success in several of the computer vision challenges. And these include the classification, object detection, autonomous driving, semantic segmentation, and the list really goes on. One thing which is very important is that before the advent of the deep neural networks, we were having different kinds of algorithms for the different kinds of applications. But now we have one kind of backbone algorithm, which is obviously we have different configuration of the deep neural networks. However, most of the deep neural networks have a very common kind of setting. So you have multiple convolutional neural network, you have multiple convolutional layers, you have fully connected layers, you have activation functions, and so on. And this has helped a lot. And the reason is that now the hardware community can focus on optimizing just one kind of algorithm and afterwards advancing the state of the art in the computations. Okay, so here we discuss the main problems. So apart from all these benefits, now we will look at the issues which the hardware community is facing. So on this slide, we are showing the top 1 accuracy of the image classification networks on the ImageNet dataset. And if you look here, on the vertical axis, we have the top 1 accuracy, and on the horizontal axis, we have the operations in the gigaflops. And the size of the circle is basically letting you know the size of the model. And when we say the size of the model, what we really want to say is that the number of the parameters or the number of the learnable parameters in that model. And what we observe is that even though there has been a lot of advancements in the way we are now designing our deep neural networks, still the deep neural networks which have a higher accuracy tend to have a higher model size. And this is something which is problematic because if we have a large model size, what it really means is that we shall be having a lot of computations. And when we will be having a lot of computations, we also need to have a lot of storage memory to store all those parameters. Okay, now when we have to implement these, so just give me a minute. Yeah, so when we have to implement all these deep neural networks on the hardware, we have multiple options, and the options include the processors and the GPUs, which obviously give you the flexibility and the ease of the use. And we have the option to use the AI accelerator chips, which are mostly based on ASICs and FPGAs. And the benefit which they give is that they allow you to have the dedicated accelerator design and give you a high performance at a very low energy cost. So as an example, for any given node, the the hardware based AI accelerators typically provide up till 1,000 times improvement in the efficiency as compared to the corresponding CPU based design. And all this is evident from the information provided over here. And this is the reason that we believe that the hardware accelerators are nicely suited for the tinyML. Okay, so moving on, now that we know that the hardware architectures or the hardware accelerators are very useful, it's time to have a look. It's time to have a look at the typical architecture of the hardware accelerators. This is how a typical bean and hardware accelerator looks like. It typically has a neural processing array and an on-chip memory. The neural processing array can be something like a systolic array. It can be an array of processing elements, and this on-chip memory is typically a very limited kind of on-chip memory. It can be as low as just 32 kilobytes. And obviously, as we cannot store whole of the model and its associated parameters in this on-chip memory, we have to store most of the network on an off-chip memory. And so what happens is that the bulk of the model parameters and the input and the output stays on the off-chip memory, and it is and you have to get it from the off-chip memory on demand. And afterwards, once it is inside the on-chip memory, it is passed on to the neural processing array to basically process it. Okay. And just to relate it with the with some state-of-the-art and some widely cited hardware accelerators, this slide is showing you the memory, the on-chip memory of these state-of-the-art hardware accelerators. And so if you notice here, the Iris has 108 kilobytes of the on-chip memory. The SqueezeFlow has 192 KB. The FlexFlow has 64 KB, and so on. So one thing which is really common in all of these hardware accelerators is that we have an extremely limited local storage. And so what it really means is that there will be a lot of shuttling in between the off-chip and the on-chip memory. So now we will have a look at this whole process in a bit of more details. So as an example, here we show the input feature map of a particular convolutional layer. Here we show the output feature map of a particular convolutional layer. And in between, we have the weights, which are obviously defined by the model. And all of this data has to be kept in the off-chip memory, which is shown over here, and which is over here in our hardware accelerator. And in the on-chip memory, we can bring only a part of this whole data. And so what we do is that we just bring a chunk of the data on the on-chip memory, and we call it as a tile, right? And afterwards, and obviously, the smaller the tile size, it means that there will be a lot of data settling in between the off-chip and the on-chip memory. And just to understand the gravity of the situation, if you look over here, for one of the hardware accelerator, which was the Cambricon, we show here that this memory access overhead can be as large as up to 80% of the total energy cost. And so what it really means is that apart from all the computations, 80% of the energy is being wasted in this off-chip memory access. Yep. So moving on, and so what we then want is to minimize this energy overhead. And one of the way is to make use of the data reuse. And what is really meant by data reuse is that, as an example, if we have brought a particular portion of the input feature map, we would like to process it entirely before moving on to the next input feature map. Similarly, if we have brought a particular portion of the weights, we have to process it entirely before moving on to the next tile of the weights. And so, considering all that, we have multiple data reuse orders. So we have input reuse order, we have the output reuse order, and we have the weight reuse order. And typically what is done is that once we have an architecture and we know all our design constraints, we have to do a design space exploration. And in that design space exploration, we know what is our model size. We know what is our on-chip buffer limitations. And what we do is that we do the design space exploration to find a tile size, which basically gives you the minimum off-chip memory access overhead. And obviously there will be a limit to the amount of optimization which one can do, and there's still a chance that even after doing the design space exploration, we have a lot of off-chip memory access overhead. And so one of the way is then to do the model compression. And for model compression, typically the pruning is performed. And when we do the pruning, there are multiple options. We can have the structured pruning and we can have the unstructured one. And for our particular case, we are doing the structured pruning. So before I move on, if you have any question, please feel free to post it in the question and answer. The question and answer portal of the Zoom meeting, okay? So moving on. So now we will move on to the SuperSlash methodology, and the main thing and the main takeaway of this talk would be this motivational analysis. So if you look here, on the slide, we are showing you the VGG16 model, which was trained on CFAR, and afterwards we generated 3 models out of it. So the model M1 is modified, is basically a compressed version of the VGG16, which is 64% pruned model as provided by one of the very famous work, Lee et al., and it was presented in ICLR 2017. And afterwards, we have this M2, which is again a 64% pruned model, which was obtained using the SuperSlash method, which we are basically proposing. And afterwards, we have this M3, and in M3, again, we are having a 64% pruned model with equally distributed pruning budget across all the layers. And if you have a look over here, we are basically plotting the off-chip excess volume, considering various different design reuse options, right? And if you look here, we have a very interesting observation. And the observation is that even for the same model, the different reuse strategies result in different off-chip memory access volume. Now, this observation is something which everyone expects, and it's not a very novel observation. But the most important one is that even for the same reuse strategy, these three pruned models require a different off-chip memory access volume. As an example, if you look here and you consider the weight reuse order, and although all these models have been pruned by around 64%, it means that they have the same model size. Even then, they have the different off-chip access volume. So it is one of the motivation which basically lets us know that it is important to intelligently select the layer from which we want to remove the parameters. So if we move on, it is another experiment which we did. And in this one, we took the VGG16, and afterwards we pruned the model by removing 0, 2.5, 5, and 7.5 K parameters. However, when removing the parameters, we either remove the parameters from the layer 6 or we remove the parameters from the layer 13. And what we see here is even more interesting. That even with the same number of parameters removed from the different layers, we can have a different impact on the off-chip access volume. So this is very interesting. And again, it gives us motivation that our layer selection for the pruning should be guided by the design requirements. Moving on. And then afterwards, we did one more experiment. And what we did in this experiment was that we took the model M1 and we did the design space exploration. And afterwards, we took the model M2 and also again, we did the design space exploration. Here, the red crosses basically represent the M1 design space exploration. And this black cross is basically when you use the M2 model on the best point of the M1 DSE. And so what you get is basically this point. And what you can see in this point is that if it is basically consuming around more than 20 megabyte of chip access volume. However, if we had done our design space exploration using the M2 model, this would have been our solution, which is basically consuming only 15 megabytes of the off-chip access volume. So what it really means is that the best design points from the design space exploration of one pruned model may not relate with the best design points from another model, and so on. And hence we need a unified methodology, which basically performs the co-exploration of a deep neural network model and its associated design space while minimizing the off-chip memory access volume. And hence with this motivation, we had this, we had this unified model compression and the design space exploration strategy. And what we do in that, we have a layer-wise ranking function, which basically ranks the layers as defined by a suitability function, and the suitability function is guided by the off-chip volume access of each layer. And afterwards, we also have an extended design space exploration in which we can have a different reuse strategy for each layer. And afterwards, we also have the possibility of the layer fusion. And when we say layer fusion, what we really mean is that you process one convolutional layer, and afterwards you do not take or write the result back in the off-chip memory. You just keep on using that output data, and afterwards you again do the processing of the next convolutional layer on it. So it is what we call as the multi-layer fusion. So let's have a look at the details of our proposed methodology. So here we have the input and the baseline deep neural network architecture. We have the constraints in which B is the on-chip global buffer size, which is basically the maximum possible memory which we can have in our design. Afterwards, we have the ATH, which is the accuracy constraints. So obviously, although we shall be doing the model compression, but our accuracy should not be dropping below the ATH. And afterwards, we can have the constraints like the maximum possible off-chip volume access. We can also have an alternative constraint like the maximum possible pruning ratio, which we have termed as this capital C. So once we have all these, and obviously we need the data set, as we might be able to do the retraining or the fine-tuning of the network. So afterwards, we move on to the step one. In the step one, we have this design space exploration, which is based on the minimum of the memory access. So this step one is something which is mostly like a standard design space exploration. However, we do have the possibility of doing this multi-layer fusion. And as I have explained, the multi-layer fusion basically means that once we have an output tile available with us, we do not write it back in the main memory. We process it further, and only once it is completely processed as per the requirement of the next convolutional layer, only then we write back the result in the object memory. And the afterwards, what we get as an output is the final layer-wise object memory access. And once we have this object memory access values for all the layers of the network, now we can do a layer ranking of the of all the layers in a manner that we start pruning the model such that in step 1 we prune the layer which has the maximum object memory access overhead, and afterwards we keep on basically progressively pruning it, and we keep on repeating all these steps iteratively, and as we move on, our model size is basically continuous. Any question? Okay, and as we move on, our model size is continuously decreasing, and in case the accuracy goes below the defined threshold, only in that case we might have to do a global fine-tuning, and afterwards we have to start the process again. In case despite of exploring all the layers, we are unable to reduce the accuracy, only in that case we have to raise our hands and say that it was the best solution which we could have had. And in that case, the last known solution, which was below the, which was basically not violating the accuracy threshold, is considered as the solution. So, and then we can also have additional constraints depending upon the basis of the pruning ratio or the excess volume. So, behind all this methodology, we have a mathematical model where we model the number of the filters, the input channels, rows, and the columns, and all the network information. And afterwards, we have to basically compute the data volume and the excess vectors, considering the different data reuse strategies. And afterwards, we basically compute the layer-wise off-chip excess volume for the single layer processing, as well as for the multi-layer fusion. And as you can understand that we have a very large design space, so we have some heuristic methods to reduce the search space so that our design space exploration do not take a lot of time. Moving on, the details of the ranking functions are basically provided in the article, and you can have a look at it from there. Now we move on to the results. So in this slide, So what we are basically showing is that we have a layer-wise comparison for the VGG16, which was trained on CIFAR. And what this slide is really showing is the details of the network and the layer-wise pruning details, right? So it is the detail of the network, and afterwards we have the details of the filters which have been removed and the flops which has been now reduced. And afterwards, we also provide the outcome of the design space exploration. So let us consider it in a bit of details. So as an example, when the hardware accelerator will be processing the convolutional layer number 1, it will be the tile size as mentioned over here. And here it mentions that for the first 2 layers, we shall be doing the multi-layer fusion. And it also explains that for each layer, we are using either ORO, IRO, and so on, right? So moving on, and what this table shows is that for a comparable pruning ratio, our model provides 49% lower memory access volume as compared to the state of the art. Again, some more results over here. So in here, what we are really showing is that these bar plots are basically showing the off-chip excess volume, and on the right side we have the pruning ratio. Now the state of the art was the VGG16 network, which was pruned by Lee 17, and the SuperSlash, and it is the outcome of the our model. And what you can see is that over here, if you consider the convolutional layer 9, 10, 11, 12, and 13, the model pruned by Lee is equally pruning all these layers. On the contrary, the SuperSlash methodology is basically pruning the layers 9 and 10 more as compared to the convolutional layers 11, 12, and 13. Similarly, if you look at the convolutional layer number 6 and 7, our model is basically pruning these convolutional layers considerably. However, the standard model, which was pruned by the technique proposed by Lee, it was not pruning the convolutional layers 6 and 7 at all. And so it basically shows that unifying the design information into model pruning is something which is very useful. Similarly, here we show our results for multiple on-chip buffer sizes. We also show our extended design space. So basically, we have a very large design space. And what we show here is that although we used some heuristics to decrease our search space efficiently, still our solution is close to the exhaustive solution. and it is something which is very useful. And other very interesting outcome of this design space exploration is that we have added the model pruning into the design space exploration of the hardware. So here again, some of the results on some other networks as well. As an example, for Mobilenet V1, which is already a pretty optimized network, it was requiring an off-chip access volume of 11.89, and after we applied our particular methodology, the off-chip access volume was decreased to 4.33 megabytes. So we demonstrate that our method basically provides lower off-chip access volume as compared to the state of the art for a comparable accuracy level. And as an outcome, which I believe is the main takeaway of this work, is that iteratively pruning the network and pruning it by basically using the design goals is something which can help anyone for their particular hardware. So with this, I conclude my talk, and I will pass on the mic to Dr. Oves for any question and answers if we have received.
Yeah. Thank you very much, Dr. Rehan, for a very interesting talk. Yeah, we have some question. So I will read out the question. Have you experimented implementing M1 model on M2? If yes, what were the results? So if you can comment on that.
Yes, I think I got your question, and let me go to the slide, which perhaps is related. Okay. Oops, sorry. I'm going back. And okay. So here we have the M1 design space exploration in red, right? And the best the best design space with respect to the M1 was which is over here, and afterwards when we use, so this cross is basically representing a particular tile size, and the particular layer wise design we use the strategy. And afterwards, when we use that strategy on the model M2, the excess volume increases and it goes to here. And what we are basically showing here is that if, on the contrary, we have done the design space exploration using the model M2, it would have been our solution. So if your question was that did we so just let me have a look at the question again. So were you asking that did we do the otherwise? If that is the question, I think the results are not over here. But yes, even if you do Otherwise, uh, the results are not optimal. So it's true vice versa as well.
Right. So thank you, Dr. Rehan. We have another question. What neural network framework was used in creating these models? How was the power consumption measured?
Okay, so we use the graphs to do all the model compressions, and we did not explicitly measure the power consumption. We basically compared the off-chip excess volume with the comparable techniques.
Right. So we have one more question. It has been shown that most of the energy is due to accessing the off-chip memory. What is the contribution of network on-chip used for dispatching the data, activation and weights to the processing elements? Is it relevant as compared to other contribution, namely computation and global buffer?
If I've correctly understood the question, let me go to the slide. I'm sorry, let me go to the architecture slide. Right. So one thing is that our particular contribution relates with the shuttling between the off-chip memory access and the off-chip memory and the on-chip. And it is not related with whatever is happening in between the neural processing array and the on-chip global buffer. So our contribution is not relating with the scheduling which is required to be done to move the data from the on-chip memory to the neural processing array. There are other kind of articles or work which basically relate with the memory scheduling in between this buffer and the neural processing array, and also the memory scheduling in between the on-chip buffer and the neural processing arrays is mostly defined by the architecture of the particular hardware. On the contrary, what we are proposing is the way the tiles can be brought from the off-chip to the on-chip memory.
Right. And any other question from the participants? Yeah, we have one more. Do you see larger memory models, the ones currently being run on GPUs, can benefit from this approach?
Yes, we believe that the larger memory models will definitely benefit from this approach. Yeah, sure.
Right. Dr. Han, also, can you comment about the multi-layer fusion? How many layers you have used, or is there any, like how many layers maximum you can use for the multi-layer fusion part?
For the multi-layer fusion part, it all obviously depends upon the design space exploration. And since we do consider, okay, so if we just want to highlight it once. For the case of multi-layer fusion, there's only one restriction. As an example, if the layer 1 and layer 2 are being fused, then the layer 1's reuse order has to be output reuse order, and the layer 2's reuse order has to be the input reuse order. And the reason is that the output of one layer has to be the input tile of the next layer. So we have only these two restrictions. Apart from it, if the multi-layer fusion is able to give you the best results on all the
like to again thank our proud sponsors, the Aeon Devices, ARM, Deep Light, Edge Impulse, EMSA Visual Sense, Greenwave Technologies, Gravity Inc., HotG, Imagimob, Latent AI, Maxim Integrated, Analog Devices, Oxo, Qualcomm, Reality AI, Renesas, SAP, Seed, SensiML, Sensense, and Senticent. And also the the software and hardware foundation for the tinyML they provide. Deep Light, they basically use AI to make others AI faster, smaller, and more power efficient. Then we have the Edge Impulse, they provide the tinyML for all developers. Also the EMSA, which is basically the I in IoT, provides Edge AI visual sensors. Also, we have the green waves, which enable the next generation of variables to process the rich data with energy efficiency. Also, the Gravity Inc., they are the software development services for the tinyML solutions. We have distributed infrastructure for the tiny ML apps, and Latent AI, the adaptive AI for the intelligent edge. Maxim Integrated, they provide the enable the edge intelligence for the tinyML. Exo Auto ML, they are the automated machine learning platform that builds tinyML solutions for the edge using sensor data. Qualcomm AI Research, the advanced AI research to make the efficient AI computing. Reality AI, they basically add the advanced sensing to your product with Edge AI or tinyML. SensiML, they build smart IoT sensor devices from the data. SynSense builds sensing and interface hardware for ultra low power, meaning the sub-millivolt enabled mobile and edge devices. Syntisat, neural decision processors or the machine learning training pipeline. So they work on the edge of silicon software and the data, which is the current need. And also, I would like to remind again about tomorrow's talk, which is at Wednesday, November 17th. The presenter is Kate Keller from NVIDIA with partners. The topic is tinyML for the good, tiny tech for the world's biggest challenges. The webcast will start 7 a.m. Pacific time. And again, I would like to thank all of you and also thank the speaker for his interesting and motivating talk, and just the copyright notice at the end. And if you have any further QA, you can just follow up on the available link or on the YouTube video, which is going to be available tomorrow. Thank you, everyone, for your participation. And again, thank you, Dr. Rehan, for his very much interesting and nice talk.